Sui is a high-performance blockchain designed around an object-centric data model that enables horizontal scalability, low latency, and safe parallel execution for a broad range of applications. Instead of treating the ledger as a sequence of accounts updated by transactions, Sui models on-chain state as a collection of programmable objects that can be created, owned, mutated, and transferred. Each object has a globally unique identifier, a type defined in Move, and metadata such as version, owner, and permissions. By structuring state this way, Sui can reason precisely about which parts of state a transaction will touch, allowing independent transactions to execute in parallel and enabling simple asset transfers to commit without the overhead of full consensus. The paper explains that Sui uses a variant of the Move language tailored for this object model. In Sui Move, resources are first-class, linear types that cannot be copied or implicitly discarded, and modules define how objects of specific types may be created and manipulated. Capabilities such as ownership and transfer are encoded in types, which lets the runtime enforce safety and variance at compile time and at execution. The object ownership model distinguishes between owned objects, shared objects, and immutable objects. Owned objects have a single owner, either an address or another object, so transactions that mutate them can be executed with a lightweight protocol that only requires validators to certify causality and absence of conflicts, not to reach total order. Shared objects, in contrast, can be accessed by many users concurrently and therefore require ordering via consensus when mutated. Immutable objects never change and can be read freely without synchronization. This segregation allows Sui to dispatch most everyday transactions, like payments or NFT transfers involving only owned objects, through a fast path that avoids global consensus and achieves extremely low latency. To support this fast path, Sui employs Byzantine consistent broadcast for causally independent transactions. A user submits a transaction to validators. Each validator executes it speculatively against its local state for the referenced objects and returns a signed effect if it succeeds. Once the sender collects a quorum of signatures, the transaction is certified and becomes final for the objects it touched. Because owned object transactions affect disjoint state, the system does not need to agree on a total order across all transactions, only on the causal history of each object. When shared objects are involved or when conflicts arise, Sui falls back to a high-throughput consensus layer. The paper describes a DAG-based mempool and consensus stack, inspired by Narwhal and Bullshark, Tusk, that decouples data dissemination from ordering. Narwhal handles reliable, scalable broadcast of transaction batches, while the consensus protocol totally orders references to shared object transactions for safety. Decoupling these roles improves performance and simplifies recovery if leaders fail. Sui's validator set is permissioned at the protocol layer but open to economic participation. Validators are selected for fixed-length epochs via on-chain staking of Sui by validators and delegators. Within an epoch, the validator set is fixed, which simplifies the safety analysis of the broadcast and consensus components. Between epochs, state can rebalance and validators can join or exit. Fees are paid in Sui and are split between validators according to stake and performance. The paper introduces a storage fund mechanism intended to align incentives for long-lived state. When users create on-chain objects, part of their gas covers not only computation but also long-term storage. Later, when objects are deleted, a rebate can be issued from the fund, encouraging responsible state usage. Gas in Sui measures both computation and I/O. Because objects precisely describe the state a transaction will read and write, the runtime can predict resource usage more reliably and schedule work efficiently. Programmers write Sui Move modules that define object types and methods. Transactions call entry functions with explicit object references, signaling dependencies to the execution engine. During execution, the engine performs borrow-checker-like checks to guarantee linearity of resources, preventing double spends or aliasing errors at the language level. Parallelism is a central design goal. With the object graph and ownership metadata, the system builds a dependency graph of transactions at submission time. Disjoint transactions, those that touch disjoint sets of objects, can run simultaneously across cores and machines. Even for shared objects that require ordering, the DAG-based consensus maximizes pipelining, and the execution engine can still exploit intra-block parallelism for independent subparts. The result is horizontal scalability. Adding hardware increases throughput because much of the workload is embarrassingly parallel. Checkpointing provides liveness, auditability, and fast synchronization. Validators periodically form certified checkpoints that summarize the effects included up to a sequence number. Light clients and new nodes can catch up efficiently by verifying checkpoints rather than replaying every transaction. Checkpoints also provide a natural boundary for epoch transitions and facilitate archival and pruning policies governed by the storage fund economics. On the developer side, Sui's object orientation maps naturally to common Web3 use cases. A fungible coin is a set of coin objects owned by addresses. Merging and splitting coins are simple object mutations, and transfers of owned coin objects can commit via the fast path without calling consensus. NFTs are immutable or owned objects with metadata fields, marketplaces that operate on shared order books use consensus for shared object updates, while minting or transferring individual items remains fast. More complex applications, games, social graphs, supply chains, compose these patterns. Player inventories are owned object trees, shared arenas or boards are consensus-ordered shared objects, and immutable objects can store static assets and code. Safety relies on the move type system and capability discipline. Modules can mint objects only if they hold or create the appropriate capability resource. Authority to transfer or mutate is similarly represented as a value passed through function calls, preventing privilege escalation via raw address control. Because capabilities are non-copyable resources, programmers are forced to design explicit flows of authority, improving auditability. The validator runtime enforces module boundaries and type rules during execution, and the consensus execution pipeline ensures that any shared object effects are applied exactly once in a consistent order. The paper also discusses failure handling and Byzantine tolerance. Consistent broadcast ensures that for owned object transactions, either a certified effect is eventually formed or the transaction is safely rejected. Equivocation or censorship by minority faulty validators cannot corrupt object histories because certification requires a quorum of stake signatures. For consensus paths, the underlying BFT protocol tolerates up to 1/3 of faulty stake while preserving safety and liveness under partial synchrony. Because data availability and ordering are decoupled, nodes can recover from crashes by fetching missing batches from the DAG without blocking the rest of the system. From a user's perspective, these mechanisms surface as two observable properties. Wallets can submit transfers and show final settlement once a certificate is formed, often within a single network round-trip. dApps that coordinate shared states still scale better than traditional blockchains because consensus operates on batched references in a pipeline DAG rather than a single leader's proposal stream. The economics and governance model complete the picture. Sui is both the fee token and the staking asset. Validators earn rewards from gas and protocol incentives, and delegators share in validator rewards in proportion to stake. Because gas captures storage over the object lifetime, applications internalize the long-run cost of state growth, and the storage fund avoids the tragedy of the commons where everyone writes to the chain and no one pays for retention. Epoch boundaries give the system clean points to adjust parameters, rotate keys, and incorporate upgrades via on-chain governance. Taken together, Sui's design addresses three persistent blockchain bottlenecks. First, it reduces latency by removing the need for total ordering on transactions that touch disjoint state. Second, it increases throughput through fine-grained parallelism guided by explicit dependency information in the object model. Third, it improves programmability and safety by embedding linear resource semantics into the language so that asset invariants are compiler and runtime enforced rather than encoded ad hoc in contract logic. The result is a platform where everyday asset transfers feel immediate, complex shared state applications remain safe and scalable, and developers can reason about authority and effects with the same clarity they use when reasoning about types. While any high-performance design faces trade-offs, such as the added complexity of managing shared versus owned objects, the need for robust developer tooling for Sui Move, and the operational discipline required of validators to sustain the DAG and checkpoint pipelines, the paper positions these trade-offs as necessary to achieve web-scale blockchain performance without compromising safety. The object-centric approach, the fast path for single-owner transactions, and the consensus architecture derived from modern BFT research combine to deliver a system that scales with hardware, matches application access patterns, and preserves the core guarantees of a public ledger. For more insights on Sui, object-centric blockchains, and scalable smart contract execution, remember to like, subscribe, and keep learning, here at Crypto in Black and White.